All right, let's talk about implicit differentiation. And the place that we're most likely to see this is in situations like this where we've got either an isoquant, which we're thinking about here as a mix of capital and labor, giving us some quantity, or an indifference curve, where maybe we think about beer and pizza giving us some level of utility. So in a situation like this, we're going to have some sort of a function of x and y, right? Whatever our x and y variables are. And it is usually the case that we can't nicely disentangle them, right? So a situation we might have for, say, this isoquant could be something like, say, the square root of k times the square root of L. In this case, we're going to have those equal some constant level of output. We'll think about that. We'll just call it quantity for the time being. And now what's going on is, rather than saying L equals some explicit function of k, we're treating L as something that implicitly varies with k, given this fixed quantity. And the tools for finding the derivative of that, for getting to the point of what is the slope, requires us to use implicit differentiation. So what does that mean? Well, let's say we're looking at this sort of a problem. I'm going to try and draw this extreme enough so that we can see what's going on. Let's say we've got a budget constraint that looks like that blue line. And we want to, say, maximize output without going over our budget. So what happens? Well, let's say we're starting here. We've got a lot of labor and not a whole lot of equipment. What we can see is that if we move this way, we're going to be moving to a different orange line. So this orange line, you might remember this from intermediate micro if you've already seen that. But the basic idea here is every point along this line is some combination of our x and y variables that holds our output constant. Right? That's why it's called an isoquant, because we've got the quantity and we're kind of isolating it in some sense to make this a fixed number. So with this sort of a function, we could call this Q1. Here we've got Q2, and Q2 would represent a higher quantity or a higher level of utility, right? If we get more beer and pizza, we move to a higher indifference curve, which is representing a greater output in the thing that we actually care about, which is maybe utility, maybe quantity if we're thinking about production, but the math is the same, right? So again, let's say we start here. We call that point A. Could we do any better than at point A? Well, if we change our mix so we get a little less labor and use that cost savings to invest in more equipment, that's going to move us to this higher level. Or maybe we're way down here and we've got a lot of relatively expensive equipment but not enough workers to run it. Then we can move in this direction, use our cost savings from our capital to hire more workers to use the remaining equipment. So, in order to find where we want to be, and the way I've drawn it hopefully makes it pretty clear, the best we can do is to go to this mix of capital and labor. We'll call that K star and L star. That is the solution to this problem. Right? So we've got some representation and we want to say maximize output subject to a budget constraint. Now, this is something that we could do with constrained optimization, which we'll see later in the semester, or we can use a convenient fact that's pretty obvious here, at least once you know how these systems work, which is the slope of our budget constraint is going to be equal to the slope of our indifference curve or our isoquant at the solution, right? So we want to get onto Q2. Now, Q2, it's going to turn out doesn't really matter if we call this Q1 or Q2 or 100 or 12,000 or whatever. Since it's a constant, we're going to have the constant function rule. This is going to turn into 0. But big thing here is we want to take this function, and we want to find, let's use Q and L. So we want to know what is the change in L for a change in Q. Right, and that's going to give us some function, change in L, change in Q, sorry, change in L, change in K. This is going to give us some function that's going to tell us how does L change as we change Q, right? So as we change K. Right, so it's going to be some function of K, and probably it's also going to have L in there. But we're going to get some function that's representing the slope, and then all we have to do there is set that equal to our Dldk from our budget constraint. So getting Dldk from the budget constraint, that's maybe a good place to start here. So the way I think of budget constraints, what fits nicely into my head is we think we've got some price on capital. Traditionally, we call that R, the rental rate on capital, times the amount of capital we use, plus the wage rate for labor, times the amount of labor we're using. And we're assuming homogeneous labor, homogeneous capital, which is not very realistic, but it's a convenient simplifying assumption. So we've got our budget constraint. Now, the easy thing to do here is to rearrange. So we want L as our y variable. So what do we get? We get WL equals B minus RK, divide both sides by W, and this gives us L equals B over W minus R over W times K. And the derivative of this to give us what is the slope, what is Dldk, well, that's pretty easy. It's just going to be minus R over W. But as long as we're talking about implicit differentiation, let's use it. So we've got B equals RK, so we're still thinking about K as our choice variable, plus W times L, and I'm going to treat L a little bit differently here. I'm going to think of L as a function of K. That is implicitly the case, right? So if we're moving along our budget constraint and we change K, well, we're going to change L, right? We can see pretty clearly this line and how we're going to get that slope out of this. But we can also basically derive in place, right? Rather than rearranging and do explicit differentiation, which in this case is a lot easier, we're going to basically say, how does the whole thing change as we change K? So we're going to do Dldk of this whole equation. And that's going to split down to Dldk of B equals Dldk of RK plus Dldk of W times L. And again, L is implicitly a function of K, right? How much labor we use, assuming that we're on the budget constraint, right? So strictly speaking, our budget constraint is less than or equal. We're just going to say, let's go on to the budget constraint. Right? And given pretty normal assumptions about the shape of our isoquant or our indifference curve, we're going to expect to be on the budget constraint. There are not many cases where your utility maximizing point is inside of your budget constraint, at least not for this class. So let's take this as it is. We'll get the easy parts out of the way. So how does B change as we change the amount of capital we use? Well, this is our budget, and this is exogenous. This is from outside the model, so that change is 0. How much does RK change as we change R? This is the amount of money we're spending on capital. So if we buy one more unit of capital, right, we rent one more machine, we're going to have to pay that rental rate. That is going to be the change in this term. Right, nice, easy R. And now here we are in the difficult part, difficult-ish, right? So now we're thinking L is a function of capital. So now we're in a situation where we want to be using a little bit of chain rule. right? So if L is a function of capital and we want to know how does this thing change as we change capital, we've got Wlk. This is going to turn into, well, let's put in an explicit example just to make it a little bit easier, right? So let's say Lk was something like k squared, right? So in that case, if L equals k squared, how does this whole thing change as we change k? Well, it's going to change by W times L prime, right? Where L prime is then representing the derivative with respect to k. And in this case, we can just substitute stuff in, right? So we're going to have W times L. Am I thinking about this right? W times L times 2k. Feel like I've done something weird here, but let's not worry too much about it just yet. So for this, what we're going to get is how much, now let's put it this way. We're going to get, we want Dldk, and that's going to be our last term from the chain rule, right? So we are going to get that. And then we're going to multiply this by, let's just really quickly give this a name, right? So let's just call this term A. So we're going to look at dA dL, right? So this really is the meat of it. And this is the part I got wrong here. This is something that, and this is a theme that you'll by now have seen a bunch in this class. It's not something that, at least for my brain, memorization really works well, right? Memorizing your way through would have maybe avoided this little error here, but understanding and working things out from first principles is how you avoid making mistakes, and it also saves you some effort on trying to remember a bunch of things in a world where there's a bunch of things we need to memorize. And of course, in this online class, you can look stuff up. You've got the internet. All right, so let's come back to this, right? So we've got our chain rule. We're thinking dA dL, right? And then the derivative of L with respect to what we actually care about with that K. Let me make it clear that that's a K. So what is dA dL? Well, that's nice and easy. That's just going to be W. And then what is Dldk? Well, we don't really know. We do know that implicitly L is a function of K, so there is some sort of Dldk, but we don't actually know what it is. But nice thing with algebra, we can just put in that placeholder for the time being, and then we can rearrange. So we got 0 equals R plus W times Dldk, right? The order is not the usual chain rule order, but 3 times 2 is the same as 2 times 3. So Dldk and W, we want to isolate this and solve for it. So how's that going to shake out? We're going to have Dldk equals, let's subtract R, and then we divide by W, and hey, check it out. We got exactly what we expected. So this was just for the budget constraint, right? So we had an easy way to get it, and in this case, implicit differentiation was a little bit trickier. But let's take a look at finding Dldk. Let me write that down before I forget. Dldk, we're going to get that from this here, right? So square root of k, that's k to the 1/2, times L to the 1/2, equals some constant q. So what happens when we take ddk of the whole thing without rearranging? So we're going to have ddk, I'm going to switch the order, dq right, which we know is going to be 0, is equal to ddk of our two terms. And even though this is relatively easy, I'm just going to kind of put in some names here right? So we're looking at ddk of a times b, and both of these are functions of k. This one explicitly, and this one implicitly. So we're looking at a derivative of two functions being multiplied by each other. Well, that means that we're looking at a product function rule, which means we're looking at a prime b plus b prime a. So we're going to have all of this stuff. Let's see, what is a prime? Well, that's going to be pretty easy. That's 1/2 times k to the 1/2 minus 1, which just turns into a minus 1/2. Don't think about this as switching the sign. Think of this as we're at 0, 1, minus 1. On the number line, we're starting with 1/2, and we are going to the left by 1 unit. Right? We are subtracting 1, and that takes us to minus 1/2. Right? So that's what's going on there. So that is a prime times b, which is L to the 1/2, right? Just the square root of L. Plus b prime times a. Well, let's get the a out of the way because that one's easy. K to the 1/2. And then what is b prime? Well, let's just use a little bit of space up here and think about what is b prime. So again, L is implicitly a function of k, right? So we want to know in this case, I guess we could call this dB dL times dL dk, right? And notice just as a matter of algebra, ultimately we can cancel out these dLs, and this is dB du, right? Which is what we are after. What is the change, or sorry, not u, k. What is the change in this term as we change k? So the dL dk, again, we don't know explicitly, but the dB dL, that one we can get. And I'll switch to green just to make it stand out a little bit. So dB dL, that is 1/2 times L to the negative 1/2, right? So this is dB dL. And then dL dk just comes down here, dL dk. We don't know what it is, but we know that it's there. And we know that it's there, and we know that we have this rest of the equation, which means that we can do a little bit of algebra and solve for this. So let's go ahead and subtract this over. We're going to have this, and then we'll divide through some stuff, and we'll figure out what we get. So we've got dL dk, which we are going to ultimately be dividing out this stuff. Right, so let's just really quickly, let's just call this C, and we'll call this D, just to be lazy. And then we'll swap them out after the fact. So we've got dL dk, C, and D. We're going to have dL dk over C equals negative D. Or sorry, dL dk times C. So we divide both sides by C, right? So we start with D plus C times dL dk equals 0. We subtract this over. We've got a minus D equals C times dL dk. We divide both sides by C, and now we've got dL dk equals negative D over C. So what is that going to equal, and what can we cancel out along the way? Well, we're going to have 1/2 divided by 1/2. That's going to be pretty easy. We're going to have an L divided by, switch to, I feel good about purple. Well, let's go ahead and write it out, right? So we're going to, I'll cancel these out. We don't need to bring these down. So we're going to have L to the 1/2, right? Minus D, so minus L to the 1/2, divided by, in this case, positive L to the negative 1/2. And then we're going to have some other stuff. But what can we do here? Well, if we've got a negative exponent, this is the same as negative L to the 1/2, right, our top term, instead of divided by the negative exponent, we can think about this as multiplied by the positive exponent. And what's that going to give us? Well, L to the 1/2 times L to the 1/2, that is going to give us minus L. Right? These exponents we're going to add together. Let me really quickly verify again, because I just don't remember this stuff. Let's say we're thinking about 2 to the 3 times, let's say 2 to the 2. Right? This is the same as 2 times 2 times 2. There's 2 to the 3 times 2 times 2. There's 2 to the 2. That's 3 plus 2 is 5. Cool. So 1/2 plus 1/2, that's 1. Awesome. What else have we got? We've got this k to the 1/2, and we've already got that negative sign here, so we don't need to deal with that again. Sorry, k to the negative 1/2. But this minus sign from subtracting d, we've already accounted for that. So we got k to the minus 1/2, and then we're dividing by c, which has a k to the positive 1/2. Now in this case, we're going to move this down, and we're going to end up with L over k. So again, this is all multiplied, so this is k to the negative 1/2, which is basically, well, here's k to the negative 1/2, and then this one we could also just rewrite as k to the negative 1/2. And again, we add these two together, we're going to get k to the minus 1, which is the same as 1 over k. So we've taken care of the k's, we've taken care of the l's, we've taken care of the 1/2s, which just cancel, right? So we could say 1/2 over 1/2, but that's just this. And then we still have that Dldk over there. So what have we got? We've got our slope, which is a function of L and K. So negative L over K, so that means, let's say we're somewhere on this 45-degree line. If we're at this point, L over K, well, this would be minus L over K, sorry. In this case, that represents a slope of just minus 1. Right? If L and K are exactly the same. Now let's say we've got twice as much K. So L over K, this is like 1 over 2. Minus 1/2 is the slope if we have more K. And if we had twice as much labor as we did capital, our slope would be minus 2. Right? So we've got a way to figure out the slope at any point on this indifference curve. And since both of these indifference curves have the same underlying thing, just different values for Q, or U if we're thinking about indifference curves. Sorry, I'm sure you figured out. I'm just going to swap between isoquant and indifference curve, but the math is the same. So I've got the slope, and I've got the slope here. Now I go back and I set these two equal and find out where is that going to be the case. So minus R over W is going to be equal to this. So minus L over K equals minus R over W. And I guess we could say minus L times W equals minus R times K. We can get rid of those negative signs. So this is just saying under this setup, under this particular isoquant, we want to be spending equal amounts of money on both in equilibrium. Right? So if we plug in some specific numbers, let's say the wage rate is $10 an hour and the rental rate per unit of capital is the equivalent of 20 bucks. In that case, we would say 20 over 10. We would plug in those prices here, and that would allow us to figure out how much labor and capital do we want. Well, we're going to have some numbers, but most important, we're going to have this ratio that tells us we want twice as much labor as we want capital given these prices. So then we can come all the way back and try and figure out where do we actually fit that in. Right, so let's see. Well, B we've just been given, Q we've just been given. So let's say we get, let's say we have a budget of $1 million. Right, so if our budget equals 1 million, And we've got this, which is really just representing, you know, let's put it this way. It's the same thing, but it amounts to the same effect. And we'll get rid of those negatives, and we'll just say, how much labor do I want? It's going to be R over W times K. All right, so now I've got a function to tell me how much labor do I want. I can plug that back into my budget, which was what? WL plus RK. So this equals W times R over W plus RK. RK over here. And then what does this tell us? Well, this tells us we're going to get our total budget amounts to twice RK. So we plug in specific amounts. Now, this is easier if we plug in numbers. I'll just say in your notes, play around with some different numbers. You can create different examples, try different exponents. Let's do a quick wrap up before we close though. The big idea here really boils down to this little thing here, right? So we've got some function and we've got our two variables, and we just treat one as though it is a function of the other, which means we apply chain rule. How do we do that? Well, it doesn't always fit neatly into your brain in terms of memory, but it all boils down to we've got some term. We ask how much does that term change in terms of the variable we don't really want, and then how much does that variable change in terms of the variable that we do want to figure out. Right? So in this case, we're thinking change in K, how does that affect L? We know that it does, and then we just go through these steps to finally isolate that. All right, as usual, if you got questions, let me know in the usual places.